All right, so with this form up, I want you to look at and check your statements with mine as far as what is given, and the justification for each one. So notice my addition property of equality here has me adding 5 to each side. And then the next line down is my combining like terms. In fact, I'm going to go ahead and scoot these up out of the way and just talk about this one for now. So you notice my addition property of equality is where I add 5 to each side, and then when the positive and the negative 5 are added together, they cancel out. So I'm combining like terms. 25 and 5 are like terms to give me 30. Positive 5 and negative 5 are like terms to give me a 0 pair and just 10y. When I divide each side by 10, it's the division property of equality. And then when I do the math, I simplify. Hey, I got to be honest with you. We get to a point where we don't necessarily show all of this math. Sometimes people want to just go from 30 equals 10y to y is equal to 3, and that correct answer is division property of equality. I divide it. If you do the math in your head, that's fine. But this is where I wanted you, if you are one of my friends who like your variables on one side of the equation, it's your symmetric property of equality that ends up being your best friend. If you wind up with your y's over here and you're like, that's just wrong, and you want to switch them to over here, the symmetric property of equality is the property that justifies your being able to do that. So this is an interesting conversation now, where I have my substitution property of equality, because what I'm doing is I'm checking my equation. I'm substituting the value for my variable in for x. And when I do that, this is my proof. So we're getting to a point in geometry where we want to make sure that we've proven that we've found the right answer. How do you know you found the answer? Because I came up with a true statement after I substituted that value from the variable in. All right, so that's our first partner. So partner 1, there are your answers. Now that we've done that, I'd like you to take a second look with your partner and going back. And what I'd like you to do is, just like I walked through and said out loud and justified and said each step and why we did it and how I want you partners to go back through, double check your work here, and talk yourself through it, justifying each step as you go. Questions? Then Marcus, go. Talk it out. You'll forgive me. All right, so let's take a look. Let's take a look at what we have. Let me see if I can find all the ones that I tossed up there. All right. This expression that I'm first given, let me see if I can find it. The one that I want first, oops, not that one. I'm going to fix that. I know this is where I'm substituting and to solve. I know this is my final answer. I know this is my given. 9 times the quantity x minus 1 is equal to 6x plus 3. And then what I'm going to do is, Then what I'm going to do is go ahead and this is where I was subtracting 6 from each side. And this was where after I combine like terms, right? I can't find the result. Oh, here she blows. There's my result of my distributive property. 9 is a coefficient, goes in front of x minus 1. Now notice, here I broke down, subtracting the same thing from each side and calling it combining like terms. So if you are able to subtract 6 from both sides, and move on to that next step, then that combining like terms happens in your head and you don't include it as a step. That's fine. All right, now I need to add 9 to each side. When I add 9 to each side, I end up with 3x minus 12. When I divide each side by 3, I get x is equal to 4. This is the part of algebra I used to tell my Algebra 1 students at the middle school, you should never get any equation that you solved wrong. Because every equation that you solve, you can check to see if you got the right answer. Take the value for the variable, plug it in, substitute that value in, and then just go ahead and simplify and combine like terms and make sure that what you get is mathematically correct. Make sense? All right, so here's what I'd like you to do. I would like you to, what's different about the way that this one's written? There's a green circle around the first hint, Sammy. What do you think? Yeah, so it's written backwards. But it's okay because your implication still starts with the if. If my allowance increases, then I can save more money. Thumbs up if you got it right. It needs to say, if my allowance increases, because that's the cause to bring about saving more money. We already talked about how yesterday the converse wasn't true. You're not going to say, if I can save more money, then my allowance increase. We already decided that wasn't true because we said you can save money by just not buying your Starbucks. You can save money by getting a job, right? You can save money if grandma gives you money for your birthday, right? So you've got a bunch of choices. So this implication has to start with if my allowance increases, then I can save more money. Questions about the implication, converse, inverse, contrapositive. Is it biconditional, yes or no? All right, when you took a look at number 2, rewrite the following biconditional statement as a conditional statement as converse. I know it's biconditional because I see the if and only if when I break it up. If you want to be absolutely 100% picky, that's going to be your P. So for your conditional, if the sum of the measures is 180 degrees, then two angles are supplementary. If you mix up that inverse converse, it's okay. I'm not going to give you a hard time. But if you want to be absolutely precise, this is your P and your Q, because the P follows the if. Okay? Considering the following statement about two angles being congruent, if and only if they're the same length, again, it's biconditional, yes, because it has the if and only if, but then we get to say whether or not it's true. The answer is yes. Hey, this is our definition of congruence. We're going to come back and use this again and again and again. Number 4, if the stereo is playing, I am wearing headphones. If the stereo is playing, I've got headphones on. Biconditional. When you wrote it, I am wearing headphones if and only if the stereo is playing. Was that a true statement? Do you think this is a biconditional? No. Hey, I had a friend in college. She used to keep her headphones on, and that was back when we had the ones that went over our heads. And she would just keep her headphones on because she didn't want people to talk to her. So she had no music in her ears. She just didn't want people messing with her and leave her alone. Do you do that? Yeah. And then one time people thought that they couldn't hear her because she's like, I have my headphones on, I'm not answering them. So they would ask her like, Jenny, 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 and she ignored them. So then they started to talk about her because they thought that, so that she heard, anyway. Drama on the dorm floor. But I think about her every time. I'm like, Jenny used to do that. Hey, I've got 3 pictures here that I think that you're interested in because it all has to do with what this conversation says. If two adjacent angles form a straight angle, then the angles are supplementary. There's a lot of vocabulary happening there. Two adjacent angles. So adjacent angles are when two angles share the same side, right? If they form a straight angle is where I have an angle that's open all the way to 180 degrees. So two opposite rays. Somebody said last class, what's the difference between a straight angle and two opposite rays? Nothing. Two opposite rays are a straight angle. So, okay, there's my 180 degrees. So if two adjacent angles form a straight angle, then the angles are supplementary. Okay, supplementary meaning adding up to 180 degrees. Hey, y'all, that's a true statement. But the picture in the middle proves why the converse is not valid. Because if 1 and 2 are supplementary, can you say that they're adjacent? And the picture proves that. Hey, that's a counterexample, okay? When we talk about a counterexample, it's a bona fide, tangible example. This is why that doesn't work. Make sense? All right, flip it over because on the back is where I really want to spend our time today. Now, when I look at number 6, I feel like I'm missing the start. I feel like, first of all, we need to be given something, and we need to know something about angles CDE and angles EDF. So I'm going to go ahead and say angle CDE and angle EDF are a linear pair. If somebody tells me something is a linear pair, and I know that's given by my diagram, that sets the stage for a higher level of accountability as far as why are we doing this, right? So this is given by the diagram. I can see that diagram. It starts off telling me that they're supplementary, and I know that's true because angles that form a linear pair are always going to be supplementary. By definition, a linear pair are angles that are adjacent, whose non-common times are opposite rays. So I know that they're going to be supplementary. All right, so then it goes through and it says that the measures of those two angles equals 180 degrees. And we have to defend that statement. How do I know that that's true? First of all, yes, it is true. The sum of their measures, here's CDE and here's EDF. I know they add to 180 degrees. How do I know it? What do you think, Summer?
The definition of supplementary.
Yeah. So what you're going to find is a lot of times if you don't know what to say about why things are true, think back to, is it a vocabulary? Is it a definition? Is it a rule that we've already been given? How do you know they add up to 180 degrees? You're like, well, that's what it means to be supplementary. That's what that vocabulary word means. The next step is huge, huge, huge. Because I go from letters of the alphabet to numbers. Okay, the X is a letter too, I get it. So I've got an X here and a 3X plus 20 here, and suddenly they show up in my proof. Who says I can do that? What do you think, Sammy? Yeah. Hey, that is another big thing. My substitution property of equality. Now, my substitution property of equality says if two things have the same value, you can write one down instead of the other. And here's the thing. Get to know these guys because you're going to see these as justifications a lot. The next word is, or the next justification is not the distributive property. Why is it not DP? Last class made that mistake. They're like, I see parentheses, it's got to be the distributive property. Serena, why is it not?
Because you don't always have to distribute.
Yeah, so there's nothing to distribute. Like there's a 1 out here as a coefficient, but if there's nothing out there being multiplied, I don't have to do anything. So my 1x and my 3x become 4x. Done.
What?
Your hands in the air.
Oh.
Yes, it was.
Well,
Who says I can put my x and my 3x together?
CLT.
Yeah. Combining like terms. You are allowed to combine like terms. By the way, I will also accept the word simplify. You're just grouping things. You're just putting things that belong together. All right, I'm going to combine like terms. What happened to my 20? Where did he go? What did I do with the 20? What did I do with the 20? I subtracted it. And I subtracted it from 180 from both sides. So my subtraction property of equality says, sure, you can take 20 away from each side. Notice the difference between subtraction property of equality and substitution property of equality. Not the same thing. Sully, how did I get x is equal to 40? What's my last step?
You divide 165.
Yeah, so I did the division property of equality. So what's interesting now is I'm looking at all these justifications that come from those notes that we went over at the very end of last class. I think at the very end of last class, let me go see if I can find them. There they are. I can add the same thing to both sides. I can subtract the same thing from both sides. I can multiply. I can divide. Our properties of real numbers are all about simplifying. And if you're curious about where the combining like terms came from, here it is. Combining like terms, simplify, find the order of operations. So when we move into this part of the conversation, that's when we start moving from the algebra to the geometry, recognizing that sometimes we're going to be talking about numerical values, and that's when we're talking about equivalence. Sometimes we're going to be talking about congruence, and that's where we're talking about things. Our proofs are going to be our 2-column or a paragraph statements that easily flow from one to the next. Now, I want to tell you something about a schedule change, so just tune in to me a little bit. You are still having your quiz today, and every single date that's on our purple syllabus is still counting, but we're like a half a day behind. And instead of adding a day to our schedule, Mr. Logan and I have decided to take a lot of the proofs out of what we're going to be doing for the test. Don't get too excited. You're still having your test next Wednesday, October 6th, but we're going to be taking a lot of the more complicated geometry proofs out of it because we have a little bit of a crazy week coming up here. You have a student holiday. We have the PSAT, SAT day for our juniors and seniors, and you guys have an asynchronous learning day. And then we have a shortened class because of the pep rally. So what Mr. Logan and I decided to do was still give the test, but we're going to remove basically the last lesson of the unit from the test. We're still going to give it to you. So our next class is a review, because the class after that is the test. And then during that week, we're going to have like a little proof boot camp. And that's what we're going to be doing with doing a lot of these more complicated proofs. So if it feels like we're skipping stuff, then you're like, wait, I'm not sure I get it. Hang on, we're sticking to right now just the algebraic stuff. And we're going to move into the geometry stuff when we have a little bit more time. Sound okay? Yeah. All right. On the back of these notes, I want you to tell me where we cut off as a class. Did we solve this one together? On the back of notes 2-4. We'll come back to the homework. Hold on. Back of notes 2-4. Yeah, we did this one, right? So we did this one. We did this one. And we got through this last one.
Yeah.
So After you finish the quiz today, I want you spending some time looking at what this third page is. I wanted to make sure that we went through and talked about those. And we'll come back and talk about these a little bit later. All right, let's get back to our homework. On the back of your homework, this next one on number 7 is definitely a little tricky. And I want you to think about what this is saying. The distance from X to Y is 42, and that's what's given. The diagram tells me that the distance from X to Z is 3 times the quantity n plus 4, and the distance from Z to Y is 3n. Where does this statement come from that tells me that the distance from X to Z, green, plus the distance Z to Y, purple, is equal to the distance from X to Y, 42? No. Yes, blue. Who says that's possible? Are they my scissors? Who says that's possible? What rule in your notes says if you have 2 little pieces of a segment, you can put them together for the big segment? Who remembers what it's called? It's not the transitive, and it's not from 2-4. So, Stan, you got to go deeper back. Who says that I can take these 2 pieces of this segment? What operation am I doing? Not, that's if they're equal. It would be the definition of the point if they're equal. Where is it in the notes? You can add 2 pieces of a segment to get the whole. No, not done in a line segment. I'll say the words. You can add, and don't forget you can do it angles. So there's one of these for segments, there's one of these for angles. With this, you can add the 2 little pieces together to get the whole. It's in your notes. It's got the word addition in it. Remember him? I expected a few more. Oh, come on, don't leave me hanging. I expected so. Oh. Yeah. The segment addition postulate says that if you have pieces of a segment, remember that was where one point was in between the others, then the distance between them, if you add them up, is equal to the whole. Remember that? And right now you have that sinking feeling where you're like, wait a minute, we got to go all the way back to unit 1. Yeah, it's in unit 1. Yeah. You're like, wait, are we responsible for everything that we've ever learned? Yes. You're like, that's so rude. Segment addition postulate can be found in the notes 1-2. Are you going to make me find them? You're the best one. Hold on. 1-2. Segment addition postulate. And right after that one, we learned his best friend, the angle addition postulate. Meaning that we can add those together. Okay, so now you know that's on your radar. All right, so then how do I again go from letters to numbers? What is the math that makes that happen? Say it out loud. Substitution, property of equality. How do I have that 3 inside, outside those parentheses, shared out to the n and the 4. What's the property called? Here's my distributed property. And then, of course, I'm combining like terms, and then I'm subtracting, and then I'm dividing. So the parts that you need to start paying attention to are up here where we're talking about the geometry, because the algebra, you're fine with. All right, turn to your partner and talk about number 8. Compare your answers. What would you add in? What would you change in your mark set go? All right, come back. So if C is the midpoint, of AD, that means that this space and this space, those distances are the same. Those distances are the same because the segments are congruent. So here we are with our given. Come back. There we are with our given. C is the midpoint of AD. How do I get to line 2? Where does that come from? It's not subco. Line 2. I heard it. Where does it come from over here? Nora? Yeah, that is our definition midpoint. So now all of a sudden, all of these things, these geometric relationships that we have, that we know are true, they're going to become rationale in our proofs. They're going to be our justifications. How do you know that they're the same? Well, because that's what a midpoint is. How do you know that they're supplementary? Well, because that's what supplementary means. So our definitions end up really helping us out. Now, here's the big thing that I want to make sure to draw your attention to. When I go from things to measures, that allows me, because this is my definition of congruence. And this is an interesting thing that we can talk about is, will I accept you telling me about it instead of the name? So if you're one of those persons that are like, I forget the name, but it's like when the segments have the same length of the congruent. So if you want to write out an explanation of it instead of the name, that's fine. You'll still get full credit. It's up to you. I will take either one. All right, again, how do I go from letters to numerical values? What's going on there? There's my substitution property of equality. So my subpo is here, substitution property of equality. And then, of course, now it's time to solve. Subtract 2x from each side. Divide each side by 6 or by 2. My division property of equality gives me a value of x is equal to 6. So I love it in the back. Sumner and Emery were already looking ahead to this one, and they're like, wait, is this going to be our angle addition property? Because look at what we have. We have this whole angle has a measure of 128 degrees, and these little pieces. What I'm asked to prove is that the measure of angle EFI is equal to 40. So let's talk about this for a minute. If I have an expression for each piece of the angle and I can add them together and I have the total, do I have enough information to solve for x? And then once I get that value for x, what am I going to do? Substitute it in and mark a set go. Turn your partner, make it work. Go.
And then number 2 is like that's something one. Number 2 is
like the angle of the So then it would be the sub. Like up here. I'm really bad at explaining it because I can't think of like the other word.
It's okay. My brain is a little makes sense, so I kind of get it.
All right, I hope you're following along. Because now I'm down to having a value for the variable. If you are one of those itchies who want your x's only on this side, then you would need to use the symmetric property of equality to switch it around. But now that I have a value for my variable, how am I going to prove that the measure of angle EFI is equal to 40? What is my next step? 4 times 10, right? So what you want to do then is go back to that conversation about how you know that the measure of angle, is it EFI? Measure of angle EFI is equal to 4 times 10. And I got that by substituting that value for the variable n. I'm so close, because you have to remember at the end of every proof, you should be looking at exactly what it asked you to prove. And you're hoping that when they say, hey, prove that the measure of angle EFI is 40, that you're able to come up with that exact statement. I do know the measure of angle EFI is equal to 40 because I can put 10 in for that x, and then I can simplify to get that value. Sound okay? So it's not going to be the multiplication property of equality because I'm not doing it to both sides. So anytime you're using your property of equality, you're seeing it on both sides of the equal sign. It's a great question. Sound okay? Yeah.
Would distributive property work?
No, because I'm not distributing anything.
It's just multiplied, right? So it's not distributed.
I'm not distributing. All I'm doing is multiplication. So whether you want to call it, you can call it multiplication, but usually we just call it simplify. That's just an operation that I do. Okay. All right. So go ahead and I'm gonna go ahead and record this if you want. The back, that last page of your notes 2-4, I want you to go back and revisit it. So have those notes out, please. Go away. On the back of notes 2-4, now that we've talked about some of the things like segment addition and substitution, maybe this will be an easier task for you to look at. Looking down here at these angles, maybe now you can start seeing some conversations between the angles that might help. I love this note down here that says your definition of congruence is going to play a major role in working with segment and angle measures. To congruent, segments are congruent if and only if they have the same measure. Two angles are congruent if and only if they have the same measure. Understanding that the biconditional that you can take back and forth. It's do me a favor and take out notes 2-5 that I left on your table. See if you can find them. So you don't have to work with the window. So on notes 2-5, we end up revisiting some things that we already know about. We already know about the vertical angle, but now we're going to put them in a theorem. By definition, we know that vertical angles are the angles created when two angles have the same vertex and no adjacent sides, no shared sides. But now we're going to talk about a theorem that tells us why those vertical angles are congruent. And when we get together next time, we're going to talk about it as a conditional statement and looking at how it is that we can prove that this is true. The congruent supplements and complements theorems are interesting because they kind of go together. Of course, keeping in mind angles that are supplementary add up to 180 degrees, and angles that are complementary are going to add up to 90 degrees. But it totally makes sense when you look at this that if two angles are supplements of the same angle or of congruent angles, then those angles are going to be congruent. And it's interesting how we can think about proving each of these sentences. So let's go ahead and take a look at the congruent supplements theorem. What this is saying is that angles 3 and angles 1 are supplementary. Angles 3 and angle 2 are supplementary. So what that means using symbols is that the measure of angle 3 plus the measure of angle 1 is going to be equal to 180 degrees. Guess what? The measure of angle 3 plus the measure of angle 2 also adds up to 180 degrees. The congruent supplements theorem saying if that's true, these two angles must have the same measure. Doesn't that just make sense? If I wanted to think about proving it, think about this. The measure of angle 3 plus the measure of angle 1 is going to be equal to the measure of angle 3 plus the measure of angle 2. I set them equal to each other because they're both equal to 180. You okay with that? Now, believe it or not, we can subtract measures that we don't even know. If I have the measure of angle 3 on both sides, I can subtract it from both sides. I don't care how much it is, whether it's an obtuse right or acute angle. If it exists on opposite sides of an equation, I can subtract it. So the measure of angle 1 is going to be equal to the measure of angle 2. I just proved the congruent supplements theorem. The same conversation can happen with the congruent complements theorem. If two angles are complementary to the same angle, they're going to be congruent. Theorems are ideas that we can prove using the postulates, definitions that we already have. And I just want to finish up real quick and talk more about the right angle theorem. There are two that you're going to be using all the time. All right angles are congruent. And if two angles are congruent and supplementary, then each is a right angle. Here's what I want you to do before I see you next. Are you listening? I want you to take a look at the back of this note sheet and jump in and see if you can finish. In addition, I gave you a proof practice, and I want you to jump in and see if you can finish. And looking at each of these. If you spend the time before class looking at and attempting these, when you come to class and I put you in a group to work on them, you'll have more to contribute. So if you get frustrated and overwhelmed, take a deep breath, relax, but think about what you need to get you on track. If you're able to figure them out, knock it out, because then that'll help your group when you come back in the next day. So the front backs of each of these, in addition to, I want you going back and revisiting the back of notes 2-4. Sound okay? Okay.